The point is that we teach you to understand the equations, not to solve them, not to be a professional physicist. That's okay. There's plenty of textbooks that do that. But if you don't want to be a professional physicist, you just want to understand, this is the place to come. Uh, it is, however, true that when I was thinking about this talk to give on it, I had a little bit of a dilemma. The previous book was called Space, Time, and Motion, and it was about classical physics, up to and including relativity, special relativity, and general relativity. So since the book is full of equations, in the talk, I could basically pick out the culminating equation at the end that was what we built up to over the whole book. Here it is. This is called Einstein's equation of general relativity. R mu nu minus 1/2 r g mu nu equals 8 pi g t mu nu. This is what tells you on the left-hand side, space-time is curved. On the right-hand side, there is stuff in the universe. Energy and mass and all those things, they give rise to the curvature of space-time, and that is what we call gravity. And in an hour-long talk, I could tell you what this equation was really all about. And I could tell you, even sprinkle in some personal anecdotes about this guy, Albert Einstein, who is largely singularly responsible for deriving this equation. So when it comes to the new book, you notice that the new book is much smaller on this slide, which is already a bad sign. But if I wanted to, I could explain sort of the culminating equation that we have for quantum field theory, which in modern physics would be called the standard model of particle physics. It's a terribly boring name for an absolutely marvelously impressive edifice that theoretical physicists and experimentalists, of course, have put together. It's hard to boil it down to a single equation, but here's a shot at doing that. It is even weirder and more intimidating looking than Einstein's equation. So I thought that I could do the analogous thing and maybe talk about this equation, and maybe I could give pictures of all the different people who contributed to this equation. But then I started writing down their names, and I got this far, and I realized, as much as I love you all, I do not want to download that many images from the internet of all these people who did this. The point is, the standard model of particle physics is a mess. It's a wonderful, marvelous mess, but it is nothing like the pristine logical simplicity of general relativity. If there are any ringers in the audience, graduate students in physics, you know when you take your general relativity course, it's hard. There are concepts you're not familiar with, but it's lovely and satisfying that you have certain basic assumptions, and then you inevitably build to the conclusion of general relativity. The standard model is just not like that. It is made of different pieces. If there are any graduate students here or professional physicists, I probably left off some of your favorites because so many people have contributed to this in so many different sets of ideas. But that also makes it very rewarding to think about. And honestly, it mostly boils down to this picture. And this is a very familiar picture. This is an atom. This is a hydrogen atom in a cartoon which is wildly unrealistic for reasons that we'll explain in a second. But it gives us enough information to summarize the basic fields that go into the standard model of particle physics. In the standard model, particles that you think of when you think of electrons or quarks or whatever, those are vibrations in fields. And forces, like electromagnetism or gravity, is also a manifestation of a field. So you have the electron over there in the top left. It is held to the nucleus of the atom, which is in this case is just a proton. It's a hydrogen atom we're looking at, by the electromagnetic force. So there's two fields right there, the electron and the electromagnetic field. Then there's the proton, which is playing the role of the nucleus here. It's made of quarks. You have up quarks and down quarks, and they're held together by the strong nuclear force carried by gluons, or the gluon field, if you want to put it that way. Sometimes up quarks and down quarks can convert back and forth into each other. That happens due to the weak nuclear force, and it will create neutrinos as well as the quarks. And then you have gravity, which pulls everything toward everything else. That's a very simple force by these standards. And in the background, you have the Higgs field, which we'll talk about more in a second. It's a lot, but it's not that much. You can grasp this, right? You could, with a few minutes, you could memorize this and write it down. But there's no tests. There's no quizzes. Don't worry about that. What we need to do is understand the behavior of these various pieces. And the reason why it's worth doing is that these pieces in different combinations explain everything that is going on in this room right now at one level. You are made of these pieces, and everything else here is made of these pieces. All the knowledge in the Midtown Scholar bookstore consists of an arrangement of particles and fields just like this. So it's worth understanding a little bit better. And the way to get there, I think, is to put ourselves in the mindset of a physicist at the end of the 19th century. So James Clerk Maxwell and Faraday and other people in the middle of the 19th century had begun to understand electromagnetism. And so that was a huge leap forward that really centered people on the idea of a field filling space. Isaac Newton had the idea of gravity back in the 1600s, but he didn't talk about it in terms of fields. Pierre-Simon Laplace later showed that you could actually think of Newtonian gravity in terms of a gravitational potential field. And also by the end of the 1800s, we had the idea of particles. We discovered the electron. We knew about atoms. We didn't know quite what the structure of the atom was, but we were getting close. So you could have forgiven a physicist at the end of the 1800s, in 1898, even 1899, for thinking that physics was almost done. We had this grand umbrella of classical mechanics, as Newton explained it to us. And within classical mechanics, we were describing two different kinds of things. Particles, which have a location in space and they're moving. Famously, according to the Laplace's demon thought experiment, if you knew the position and the velocity of every particle in the universe, you could predict the future. Exactly. But then you also had fields. The fields fill space. That's what a field is. A field is exactly the opposite of a particle. A particle has a location. Here it is nowhere else. The idea of a field is that the field is everywhere. At every point in space, every field has a value. The value might be 0, but at every point in space, there's a value for the electric field, the magnetic field, the gravitational field, and so forth. And the basic picture would have been that matter is made of particles, the table, the chair, stuff like that, just a bunch of particles in different arrangements, and the forces that had matter interacting with itself were mediated by fields. Magnetism, electricity, gravity, etc. So all that would be left in the mind of our hypothetical end of 19th century physicist would be to figure out what all the particles are and what all the forces are. Then we could put them together and we'd be done. Physics could go home. That's not how it worked out, of course, for various reasons, a big one of which is called quantum mechanics, which first kind of hinted at in 1900, Max Planck and blackbody radiation, but really was kind of finished between 1925 and 1928. So indeed, next year, I think there's a move afoot to call next year the year of quantum, because it's the 100th anniversary, the first really reliable theories of quantum mechanics. And in the new book, I talk about quantum mechanics. If you've read my previous book, Something Deeply Hidden, you might think that I bang on a lot about the interpretations and the foundations of quantum mechanics, but that's a different book. For these books, we're playing the role, we're putting ourselves in the boots of a hard-nosed physicist who just wants to be able to make predictions and test them against experiments. So I will give you the standard spiel about quantum mechanics, which says something like the following. That picture of the atom, this is a helium atom that we have on the left here. Similar, though, to what we had for the hydrogen atom before. Now there's just 2 protons, two neutrons, and 2 electrons. That picture is not right, even though we still always use it as the symbol of science, right? But it can't be right, according to quantum mechanics, because according to quantum mechanics, electrons aren't actually particles. They're not little dots. An atom is not like the solar system, with the nucleus as the sun and the planets as particles. The electron is described by something called a wave function. Another truly boring name for an absolutely central idea in modern physics. But the idea is that rather than having a location, the electron is spread out. And this is not a field. It's a whole complication that we go through in the book. But the wave function is a quantum mechanical essence of some sort. We don't agree within the physics community. That's why I need to write a previous book talking about those controversies. But we do agree on what to do with it. The wave function in an atom, if you took a chemistry class and you learned about orbitals and things like that, those are just wave functions of electrons in atoms. And this is a reconstruction based on data of the particular wave function that an electron could have in a particular kind of atom. They took images of it over and over again. And you need to take images of the atom over and over again to make this picture, because quantum mechanics is weird. Because quantum mechanics says that the electron is described as a wave function when you are not looking at it, and then when you do look at it, it looks like a particle. Sometimes in discussions of quantum mechanics, you'll be taught about the weird duality between waves and particles and so forth, but you're not told the answer. I just told you the answer. They're waves when you're not looking at them. They're particles when you look at them. This should be unsatisfying. What do you mean, look at them? Why should they care if I'm looking at them? What if I don't have very good eyesight? This is the quantum measurement problem, and we don't discuss it in this book. I just tell you, like a student in my second-year undergraduate class, you can calculate that, and then you can put it to work. And the work you put it to is, the wave function tells you the probability of measuring an answer that you ask of the electron. Where are you? How fast you're moving? Whatever. The probability of getting an answer is calculated in terms of the wave function. That's what quantum mechanics says. This could annoy you for various reasons. The fact that it's probabilities rather than certainties might annoy you a little bit. It annoyed Einstein a little bit, but he got over that. That was not really his worry. His worry was more that no one could tell him whether these wave functions represented reality or not. And he kind of cared about reality a lot. You can use them to make predictions, but physicists don't agree about whether they're real. I know the right answer on that one, but that's a different talk, so I'm not going to tell you. This is the quintessential idea of quantum mechanics applied to particles, okay? Quantum particle theory. We quickly had to move on to quantum field theory because we knew fields existed. We knew about the gravitational field, the electric field, magnetic field, etc. We clearly needed a quantum theory of that. It came very, very quickly. We started to think about it. We took electromagnetism and we so-called quantized it. And out of that pops photons, particles of electromagnetism. And that was kind of weird. Because sometimes, if you're taught about quantum mechanics, you get the impression that quantum mechanics says the world is fundamentally discrete rather than smooth, right? The real numbers are smooth. There's every number between minus infinity, infinity. The integers are discrete, 0, 1, 2, minus 1, minus 2, minus 3, etc. The word quantum means discrete. So I forgive you if you're under the impression that somehow quantum mechanics says that nature is discrete. It truly does not. It says that nature sometimes behaves in discrete-looking ways. That is a subtle but important distinction. It is like plucking a guitar string. You have a guitar string tied down at both ends. You can pluck it and it makes a note. But that note corresponds to what's called the fundamental frequency of the string. The string sort of uniformly goes up and down with some frequency and therefore gives you some note that you hear. But if you're a good guitarist, you can coax other notes out of exactly the same guitar string doing exactly the same thing, because there are harmonics. There are ways the guitar string can vibrate where half of it's going up, the other half's going down, and that vibrates at twice the frequency. It has half the wavelength, twice the frequency, and so on down the line. We don't need to know about the mathematical spacing between these. We're not doing music theory. What we're doing is pointing out that the string is entirely continuous. Except the fact that it's tied down at either end, the value of the string can be anything at all. The shape that the string is in could be anything at all. But in fact, the behaviors that you see, or hear in this case, of the string, come in this discrete set. And any behavior can be thought of as some combination of this discrete set of ways to vibrate. So that's an example of apparent discreteness coming out of underlying continuous behavior. And that is all that quantum mechanics is about.